This is a continuation of lesson 3.2.2 loads and load paths. Let's just look at different loading types. The most common type of loading that we're going to be looking at is this uniformly distributed load, where we assume that roughly the same number of pounds per square foot is happening wherever you are on the surface that you're looking at the loading for. The other type of load that we may need to consider would be a concentrated load. That's when you have one piece of equipment or something that you know is going to take up a lot of, is going to be a larger load and warrant some consideration that's located in a specific location. That would be called a concentrated load. These are some examples of load combinations, and what's going to happen is you're going to go into the building code, and the building code is going to say for your occupancy type you need to consider this load combination, or you need to look at these different load combinations and see which is the worst case scenario. So here's some examples of load combinations that you may be calculating. So perhaps the building code will say if you have your dead load plus your live load plus your roof live load, or your snow load or your rain load. Calculate that and then maybe compare it to the dead plus the live plus the wind. See which of those is largest and use that. The third example here is dead plus live plus snow plus the earthquake load divided by 1.4. So you'll just have to rely on what the building code is asking you for and go with whatever that is, but it'll probably be set up as a load combination. So those are some of the design loads that we are going to need to consider. Again, the building's dead load is the only load that you can, with some certainty, calculate, because you actually know how heavy each of those girders are and the different components that are making up that dead load. You can actually figure out the actual weight of each of those components and add those together. All the other forces will vary in magnitude, duration, and location. The building is designed for a design load that may never occur, but is designed to be safe, and so a lot of possible situations are taken into consideration. All right, we're going to move on to something called load paths now. And so let's just talk for a moment about what tracing or chasing the loads is. So if we look at this building here, let's assume that we have this weird two-dimensional building. And if we start at the top here, let's assume that this little form up above here is some snow. So we have some snow that is giving a load on the top, a snow load on the top of the roof here. And then we have the roof itself and the weight of the roof. All right, so those are the first two things that we're going to consider. And those two components there are going to be the first bit of load that we're going to look at the load paths and see how those are chased down. So those first two, this arrow is representing that those loads are kind of held up at this corner here. And this corner is in turn held up by this column right here. But that column also is holding up, assuming that things are evenly distributed on this floor here, roughly half of this floor is going to be, the load is chased. The load path is heading over to this column here. So this column right here is holding up all of this stuff up here. All right. In turn, this column then is being held up by this column here. And so this column that I just circled here is holding up the column above it, as well as all the stuff above that, as well as roughly half of the floor here, which will chase in this direction over to this column. So as you can see, we start at the top and calculate what the dead and whatever other loads are, and then we work our way down, and with each level that we go down, we have a whole pile more loads. So if you notice, this bottom column here is a lot thicker. If you could imagine this building maybe 10 stories high or something, imagine all of the weight that the lowest columns would have to be supporting. So all of these arrows are showing us how these loads are chasing through. We get down to the main level here, and we have this much thicker column holding everything above it. And then we have a little bit more floor here. And so the final place that those loads are chased is down into the foundation, which in turn will chase the load into the soil dirt, ground, bedrock, whatever it is that the building was originally built on top of. And so that is how load paths work, and we'll talk about chasing that load through the building. And essentially what you want to do is take all the loads from the building and work your way down, and in the end those loads should be all transferred into the foundation and from there into the ground. So here's the Keystone Library, and so now you can see in 3D kind of what's happening there with this load chasing. So if we look at this green arrow, and this green arrow from here, the loads that are placed on this girder by this green arrow are chased in both directions because it's kind of centered. Let's go this direction here. It heads down to, I guess this might be better called a beam, to this girder over here. And then from that girder it gets chased down to this column, and then from the column to the footing. So just to clarify there, this whole girder and beam conversation, when we have these great big structural members that are lateral members, we're going to call them girders. And girders are a more robust type of a beam that supports smaller beams. All right, so let's see. All of these structural elements that we're going to talk about as we have things chasing through, starting with the roof deck and the slabs, which are the floors on the different levels, then to the load-bearing walls, through the connections, beams and girders, to the columns and to the footing. And so these are kind of in order of how this all is actually going to be chased through, but these are the terms that we're going to be using as we discuss these, the loads being chased through the building all the way down to the footing and then into the ground from there. This is a nice definition here. I like it. It encompasses the whole load chasing pretty well. So the structural design is performed by chasing the loads of the dead and live load from slab to beam to girder, then onto the columns or walls. The loads are then carried down to the footing or foundation walls, and finally to the earth below. So here is just again how the terminology is going to be used. So these are the girders. These are the larger, more robust beams, and then the in-between ones we'll just call beams. So girders are basically big beams that hold other beams. All right, column, I think you got that. That's not too difficult. Footing, that works. Okay, now we're going to go on to a concept called tributary area. So let's say we're looking at this area right here, and we're looking at these beams, and we're trying to figure out how big these beams need to be. What we need to do is we need to figure out how much of the floor do each of these individual beams need to hold. So if we look at one of these individual interior beams, we can calculate the tributary area. So this red area that's parceled out here, that's the tributary area. So the tributary area for any beam is going to be the total area where loads are being chased from the floor into that beam. So you can imagine that this is sort of the halfway point between this beam and this beam, and so all the loads on this half are chased down into this beam, and same goes for the other side. All of these loads are chased up into this beam. So this beam is basically responsible for this section of floor here. Those arrows kind of show you what I was talking about there. And in order to calculate the tributary area, you want that tributary width and calculate the floor loading that ideally you would have. So the little example here is, assuming the floor system must support its own weight of 40 pounds per square foot and a live load of 100 pounds per square foot, what is the uniform load applied to the beam? All right, so the total floor loading there was the 140 pounds per square foot, and so then we have the floor load times the tributary width is the pounds per linear foot. So PLF is pounds per linear foot. All right, so now if we look at these beams are supported by these girders. So these larger ones here are the girders, and they're holding up the beams. And so in order to calculate each of these girder loading, we need to figure out the tributary width for the girders. And so for each of these interior girders, the tributary width will be the girder itself and then halfway to the next girder over. And so that there would be the tributary width of those girders. Sorry, let's go back for a sec. So that right there would be the tributary area for the girders, and so the tributary width would be, you're going halfway this way, so half of 18 plus half of 18, so 2 times half of 18, we're just back to 18. So the tributary width of the girders is going to be 18 feet. And now for these interior columns, the tributary width for columns is just going to be from the column that you're trying to figure out the tributary width, or the tributary area, halfway to the next one. So if we have a column here and a column here, it would be a line kind of along there, a line going down there, over, and sort of up there. That there would be the tributary area of that column. So that column is responsible for supporting that whole section of floor, along with those parts of the beams and the girders and the whole mess that's up on top of that column there, floor, beams, girders, that falls within this area here. So that would be the tributary area of the column. And the dimensions are pretty straightforward to figure out if you have the dimensions of the building. So half of 20 plus half of 20, but then times 2, that would be the tributary area for, well, that would be the one dimension of the tributary area, and the other one would be basically 18. Half of 18 plus half of 18, so 18 in this direction. So that's how you figure out the tributary area of these interior features. And I don't believe this PowerPoint goes on. I'd just like to explain to you how to calculate the tributary area of, let's say, a corner column. So this column here, if you want the tributary area of that, it's just going to be half of the distance to the next column in both directions. And so it's actually going to be a quarter of the tributary area of one of the interior columns. And then if you have a column that's on the side here, it's just going to be half of the tributary area of one of the interior columns. So assuming that this is an exterior wall here, that's what how you would do the corner and the side column. Same with, let's say you have a girder. This girder here is at the edge of the building, and so while the interior girders, let me just switch the color. Okay, let's do green for girders. Okay, so the interior girders are going to have this tributary area. Oops, that went a little bit big. Maybe not quite that big. Okay, so the interior girders will have that size of a tributary area. The girders that are along the side of the building, they're only going to have half of that tributary area. All right, so it's getting a little messy, but hopefully that makes some sense. And same with these beams. The interior beams will have a full tributary area. Any of the beams that fall right on the edge here are going to have half of the tributary area.